Good morning. Hey, Wednesday, 5/20/20. I guess it's a good vision day, 2020. All right, time for some earth science. Today, we are going to look at states of matter. So I'm going to want you to be able to name and describe 4 common states of matter. And I want you to be able to name and describe 6 state changes, where one state changes to another. Now, why am I putting it in this chapter? You know, we got a little chapter on water, right? Well, water is one of the very few substances that we are familiar with as a solid, as a liquid, as a gas. I doubt that you could easily come up with other examples that you are familiar with as a solid, a liquid, and a gas. Okay? We could look at things around us. Here's one of these masses. It's made out of steel, I think. Okay? Possibly brass. And I'm familiar with it as a solid. And I understand I could heat it up and turn it to a liquid. But the concept of turning this into a gas really seems pretty foreign. Okay, we just don't see that. Carbon dioxide is something that's in our air, we experience as a gas, and I have seen dry ice, which is solid carbon dioxide. I've seen it as a gas, as a solid. I have actually seen carbon dioxide as a liquid, but it's not something that we ordinarily see. It's just not very many things. And water, we're familiar with. We live in Wisconsin. We see frozen water every winter. Even in the summer, you go to your freezer. We see liquid water around us, and you can't see gaseous water, but we see the results of gaseous water. We're familiar with water turning into a gas. So water is kind of unique that way, along with many other ways. So that's why I'm looking at this in this chapter. So how do we tell a solid apart from a liquid, apart from a gas? How do I know that this is a solid? How do I know that the stuff in there is a liquid? And you can see right here, I think you can see in the video, the liquid stuff jiggles around. Look at that. If I take this and I turn it sideways and you say, well, it's the same shape, you just rolled it on its side. But if you look at the water in here and you look at it now, that's a different shape. Water doesn't keep its shape. Liquids don't keep their shape. Solids do. One of the properties that helps us tell solids from liquids is shape. Solids have what we say is a definite shape. This object keeps its shape. It doesn't depend on its container. If I hold it in my hand, it's got this shape. I set it on the table, it's got a shape. I drop it on the floor, it's got a shape. Now, can we ever change the shape? Yeah, with enough force, we can change this. But on its own, it keeps its shape. Liquids don't. So we say they don't have a definite shape. They take the shape of their container. So let's take it a step further. Let's think about gases. Do gases have a definite shape? I think not. I think gases take on the shape of their container. So that lets us tell solids apart from the other two. How are we going to tell the other ones? We need something else. What's different about a gas compared to a liquid? And I've had students tell me, well, you can see liquids, you can't see gases. Not true. There are gases we can see. And there are some liquids that are hard to see, depending on the circumstances. So that doesn't quite do it. And to save time, I'm going to just get into it. The other property is volume. Solids, okay, I could measure the volume of this object. And if I put it on the desk, or put it on the floor, or put it outside on a picnic table, this object essentially keeps its own volume. Okay? Its volume is constant, its volume is definite. Liquids. I have an amount of liquid in this graduated cylinder. It looks to be just over 80 milliliters. Now, if I took that liquid and poured it into a different container, I would expect to have 80 milliliters in that other container. If I poured this on the floor, I would expect to have 80 milliliters on the floor. The volume of the liquid stays constant. When we get to gases, not even the volume is constant. Gases are compressible, okay? So I can take, with the right equipment, I can take air and just pack a whole bunch of air into a tank to put on my back and then jump in the water, and I have already done it where I've been breathing off of that tank of air for over 2 hours underwater. Now, if you just looked at in this room, that container, certainly I would go through more volume than that in 2 hours. But in the case of gases, I can squeeze more gas in that container. So the gas is denser in that container. It's crammed together more in that container than it is out here. If we knock the valve off that container, that gas comes leaking out. Okay? So the volume of gases is not definite. Gases take on the volume of their container. Now, I've got another column over here, and it's titled Kinetic Molecular Theory. Kinetic means moving, okay? Molecular refers to little particles. Theory means it's an explanation for how we understand our matter and our world around us, okay? So kinetic molecular theory says that all matter around us is made of little tiny particles that are moving. And we can understand the behavior of a lot of things by thinking of matter as little tiny particles that are moving. Okay, so kinetic molecular theory is about what the particles are doing. So what are they doing in a solid? Not much. In a solid, I'll read this off because I know it's a little bit small. Particles are low in energy and packed very close together. So close that they can't move past each other. So imagine I'm a particle in a solid, and I'm just packed in here with a whole bunch of other particles. There's a particle here and here and here and here and here. There's particles all around me. Now, I got a little bit of energy, and I move, and I bump into another particle. And I bounce off, and I bump into another particle. And I bump into another particle. So all I can really do is kind of just oscillate right around here. I can't go anywhere because we're just packed too close together. It'd be kind of like if we took the whole class, put you in the side closet, and said, "Okay, move around." And you're packed in there. You can't go anywhere. That's how we think of the particles in a solid. So what happens when we go to liquid? Again, I know this is small, so I'm going to read it to you. Particles have more energy than in a solid, and the particles are a little further apart from each other, just far enough that they can slide past each other, and the liquid can flow. So, I think I've shown this before in class as a demonstration, but imagine that we got lots of particles. Imagine I got a particle here and a particle here, and I'm moving around bumping, and now we increase the energy, so I start moving faster, and I bump these particles harder, and as I'm bumping into them harder, effectively I push them away from me a little bit, which gives me a little bit more room. So that's why liquids have a little bit more room between the particles. Now, if I got a little bit more room, it could happen that there's just a little bit of space between the particle here and the particle here and myself, and if I'm moving this way, I slide in between those other particles, and now the particles can flow, and so we can have water that flows. I don't know if you can see that or not. All right, so then what's a gas? Particles have more energy than liquids. They have enough energy to completely overcome the attractive forces that hold together liquids and solids. So the particles are spread relatively far apart from each other. See, there's another part of this that I haven't explained. Not only are the particles in a solid and liquid packed kind of tight together, but they're attracted to each other. They're holding on to each other. Okay? When we talked about the polar nature of water, we said polar molecules are grabbing hold of each other. So these particles are holding on to each other. Now, in order to tear them apart from each other, we need more energy. And so in the gas, we've gotten to the point where there's enough energy that the particles can all get apart from each other. I got another state of matter at the bottom here. And you may remember when we talked about stars and our sun, we talked about a plasma. So I do want to include that. What does a plasma look like in terms of shape? No definite shape. Volume? No definite volume. So from those two standpoints, it's just like a gas. Where plasma differs is in the particles. Plasmas are so high in energy, they're a gas-like in terms of shape and volume, but the energy is so high that the atoms start losing electrons. The electrons on the outside, the electrons start getting stripped off. And that leaves us with charged particles. And charged particles behave differently from neutral particles. So the difference, really, we could say between plasma and a gas is charged particles, neutral particles. All right, I've got don't know how well this will show up on, or maybe it just doesn't want to work. Give me a second. Oh, it's coming. All right, so here's just a model found online. So here's a solid, and if you watch it over time, you can see these particles just kind of wiggling a little bit, but they're not going anywhere. Here's our liquid, a little more energy, particles are bouncing around a little more, they're flowing around each other some. Gas, particles are far apart from each other, they collide once in a while, but mostly they're just going and doing their own thing. All right, so I want to talk about these states of matter in terms of energy that the particles have and attraction between them, okay? Now, if the particles are all clinging together tightly, that's going to lead to liquids and solids. If the particles can get apart from each other, that's going to lead to gases. What determines if they get apart from each other? Well, how much energy they have. The more energy they have, the more likely they are to be a gas, because they'll have enough energy to overcome the attractions. But what about these attractions? The stronger the attractions, the more likely we're to be in a liquid or solid state. Okay? So water is an example of having really quite high attractions between the particles. So that's why water stays in the solid liquid state to such high temperatures. Some other things like, the oxygen in the air we breathe has very, very little attraction between the particles. So these particles have enough energy to get apart from each other at, it's almost negative 200 degrees Celsius, negative 190 something Celsius. It's a competition. The stronger the attractions, the more likely we are to be in a denser state of matter. The higher the energy, the more likely we are. So what can we take from this? I know if I have a high energy and low attraction, I'm going to be in the gas. And I know if I have a low energy and a high attraction, I'm going to be in a solid. What I can't tell is, what if I have high energy and high attraction? That's kind of a mystery, and you'd have to look at the individual substance. So, all right, here's little Sally, wants to get to her house, and there's a horde of zombies in the way. Okay? And the zombies are trying to grab a hold of her. So I want you to imagine the zombies are like liquid. The particles are kind of close together. They're attracted to each other. Sally's in the gas state, right? She wants to do her own thing. Okay? What's going to determine if she can get to her house? One, how much energy does she have? Because the faster she moves, the less chance they have to grab her. Two, how strong is their attraction? If we're talking, zombies with stuff falling off, their attraction maybe isn't that strong, and she can maybe get away. All right, so it's a competition. It's kind of like, Sally and the zombies are playing Red Rover, let Sally come over. Okay, the more energy she has, the more likely she's to bust through that line and keep going on her own. The less energy she has, the more likely they are to catch her. Likewise, the stronger their attraction, the more likely they are to catch her. The weaker their attraction, the more likely she is to bust through. It's a competition. So let's talk about the names of the state changes, because matter doesn't just exist in one state. I can take water and I can turn it into a solid. I can take water and turn it into a gas. I can take a piece of aluminum and turn it into a liquid. I can change things, and there's names for these state changes. Some of them you are very familiar with. A liquid turning to a solid. Well, just think about that for a second. You're familiar with liquid water. You've seen it turn into ice. What do we call it when water turns into ice? Freezing. Okay, you know that one. So these aren't necessarily that complicated in terms. What do you call it when a solid turns to a liquid? When an ice cube becomes a puddle? That's called melting. Okay, so two of these, boy, everybody ought to get right. How about some of the other ones? Liquid changing to a gas. Sometimes students will say, or a lot of times the students will say boiling. And boiling is in here. The problem is the actual state change is called vaporization. And that's what I want you to work on for your questions. Vaporization. Now, vaporization can happen in two different ways, and they're called boiling and evaporation, and we'll come back to that. Vapor is kind of another word for a gas, and so vaporization, to vaporize, means to become a gas. How about gas to a liquid? Imagine it's a hot, muggy, humid summer day. You've been out working in the garden, and you sit down to have a break, and you have this nice cold glass of lemonade. And the glass of lemonade gets all wet on the outside. And it's not the lemonade climbing the glass to escape. It's that there's water vapor in the air that hits the cold glass, slows down, turns to a liquid. Gas to a liquid is called condensation. And so our glass gets covered in condensation. We got two more that we're not as familiar with, okay? But sometimes solids can turn directly to a gas. The name for that is called sublimation. Okay? If you had dry ice, solid carbon dioxide, it's called dry ice because it doesn't melt. You put it out on a table, it turns directly to a gas. It sublimes. Okay? And our word for gas to solid, we're going to use the same word we had in our rock cycle chapter when sediments get deposited into a new area, deposition. You can think about the gas particles get deposited on a surface. Okay? Now, of all these, some of these, you have to take energy out to make them happen. And some of them, you have to put energy in to make them happen. I mean, how do you melt something? You got to warm it up, right? You got to put energy in. How do you freeze something? You got to take energy out. How do you condense it? You got to take energy out. So these three over here, we got to take energy out. And the word for taking energy out, or energy traveling outward, is called exothermic. These over here, you got to put energy in. That's called endothermic. Okay? Heat lost, heat gained. Now, how are we going to remember that? I want you to think, down the hall, there's a door to school. Okay? Now, if you're leaving school, we call it the exit. In a fire drill, you got to head for the exits. Exit, EX, exo, EX, means outward. Okay, you go out from the exit. Now, if we're coming to the building, we don't talk about walking in the exit. We talk about walking in the entrance. Entrance, EN, endo, EN. Okay? So try to think about that. That EN, endo, entrance, that's inward. We got to put heat in. EX, exo, EX, exit, that's outward. So these processes give off heat, or we got to take out the heat. And these processes, we got to put in the heat. Now, I know some people seem to think it's really strange to think of freezing as being exothermic. You know, we're saying it gives off heat. But you have to take the heat out in order to make an ice cube. You know, the ice cube has less energy than what the water had, so you had to take it out. It's outward. Here's just a little diagram to talk about deposition. If you think about, let's say I had particles in the gas, and then I had a cold surface. And I'm comparing it kind of like the flies in a piece of fly strip. And as the particles hit the cold surface, they stick to it. And so you'd have a... So if you've ever woke up in the morning and there was frost on the car out in the driveway, how'd the frost get there? It likely went from a gas to a solid without going through a liquid state. It was deposited there. And then let's look at boiling and evaporation. So they're both types of vaporization. They're both liquid changing to a gas. There are two key differences. And the differences are in where they happen and what conditions they happen in. I sprayed a little bit of water on the floor here a little bit ago. You know what? I'm probably not going to wipe it up. And I'm pretty confident that when I walk into my room tomorrow, it's not going to be here. And I don't think anybody else is going to wipe it up. It's going to evaporate. It's never going to get hot enough that it'll boil. It's going to evaporate. So evaporation doesn't really need special conditions. Boiling does. Boiling happens throughout the liquid. Bubbles are happening all over the place. Evaporation only happens at the surface. So kind of think about it. The particles in the liquid have a variety of energy. Some of them have more energy, some of them have less energy. Some of them have enough energy to become a gas. But chances are they're going to bump into other molecules, kind of like bumping into the zombies, and the zombies grab hold and don't let them out. But what if you had a particle that was right on the surface, had enough energy to escape, and happened to be moving the right direction? That particle evaporated. Okay? Over here, we're heating this up until the average particle has enough energy to start escaping from the rest. Okay? So, in words, boiling requires certain temperature and pressure conditions. Boiling is not only about temperature. I can boil water by reducing the pressure. I can boil water at room temperature, and I have done it in my room several times. Maybe I'll consider that for one of the things I could show next week as just kind of a fun example. If I could set things up and get the camera so that I can boil water at room temperature. But boiling, okay, boiling requires certain temperature and pressure conditions. Evaporation can happen really at any temperature or pressure conditions. It'll happen faster if it's warmer. It'll happen faster if it's low pressure. But it doesn't require certain conditions. Boiling happens throughout the liquid. Evaporation only at the surface. And I wasn't going to do those last two terms, so that's our water unit. So I'm going to give you a few more questions based on the notes we just had. As always, if you have questions, let me know. Keep up on your day-to-day work. We got a little over a week left. I know when we get to June, you've got to turn in your Chromebooks and stuff, so I don't imagine we can be doing much then. But next week, we're still doing some schoolwork, so be prepared. Take care.